Take a look at some example. Here we have a tentative neurons here. Tentative neuron values here. For example, we have a 8, 1 8. One is maybe here 3, 8. We're gonna check a okay, 0, and here we're gonna check -2. We're gonna check minus 8. Okay, we'll check these values and how the sigmoid shift the value from linear to non-linear. And these neurons receive non-linear numerical responses when activated by a functions 10h, and here sigmoid, ReLU, and ReLU. Here ReLU. So you say ReLU means rectified linear unit. Rectified linear unit, ReLU. This network will always be equivalent to a linear. ReLU means rectified linear unit, and this is what you see here. As we know from a regular linear neural networks, linear neural networks always be equivalent to a linear network with a single neuron, regardless of how complex input neurons are nested and fed into the output neurons. A neural networks without activation function, as you see here, for example, so here, now these activation functions cannot represent complex nonlinearity between the input and output trend, and thus, okay, so the x-axis representing sum of weighted inputs and bias, or that's the tentative neural values, are passed through the activation function, then the results will be nonlinear or squashed or bound by the activation function. Otherwise, your line, your output will be straight line, which is not linear, which is not squashed, which is not bound, so that they cannot properly reflect the nonlinearities that exist between most input and outputs. So that's a very handicap. So we need to consider the activation functions. As you see, the most famous activation function is 10h and sigmoid and ReLU and ReLU. We have a bunch of other activation functions that you have to choose depending on your data complexities and data nature. So the neurons of each ANN layer takes the weights and inputs and bias of the previous layer. However, they will not fire up to a certain point until weighted inputs and biases reach a sufficiently high influence. An activation function will make a network nonlinear by squashing the neural outputs at the end of each layer in a way that is similar to human brain. Networks are linear until activation functions are added. Okay, so let's take a look at the activated function based on the given x values here. Okay, now let's take a look at activated value for given x-axis for example. Let's assume that we have number 8, and number 3 and -2, -8 as a tentative neuron value, or as sum of weighted input and bias, weighted by the weights, of course, here. And if you have 8, that value should be 1 here on both sigmoid and 10h. 1, 1, that's all 1 here. even if you have 8 here. Okay, and what about if you have 3 in both here, 3 here, 3 here? The sigmoid will give you some number a little less than 1 here, isn't it? Whereas you have almost a number close to 1 with a 10H. So that's the difference between these two activation functions. If you have a 0 x-axis, then you're going to have around 0.5. If you have 0, then you have 0 here with the 10H. Whereas you have, if you have -2 for x-axis, you're going to have a point around 0.1 here. Whereas you have -2, so I say -2, you have a 0.1 here for sigmoid. If you have -2 with the x-axis, you have, it's like -1. And if you have big number 8, -8 and -8, then you're of course approaching to 0 for sigmoid and -1 for 10H. This is what happened. But the activated value is quite different. If you take a look at ReLU for 8, you got 8. Okay, you got 8. In 3, you got a 3 because they are linear and positive reasons right there. Positive tentative neuron value or some varied input and bias. And if you have a -2, -8, all it'll give you 0 for ReLU. Whereas you have a same value for positive reason because you are representing positive reason with the same equations y equal x. But if you have a -2, then your value provided by Ricky is a little less than and 0, which is negative value. If you have 8, it's going to be a little lesser than this value, which is corresponding to -2. It is corresponding to -8, and it decreases with the slope of 0.01. This is the decreasing rate, right? So this is what will happen if you use leaky value. So all the x-axis represent tentative values or sum of weighted input and bias, and there's a corresponding activated value which indicates your system is now nonlinear, squashed, and bound. This is what is very important to represent your nonlinear relationship between inputs and outputs. Okay, let's take a look at one real example that we're gonna get here pretty soon. But I wanna explain how the activation function works with this example. We have here 4 neurons, of course. Of course, these 4 neurons receives a value from all previous neurons, which is input neurons. So you go in here, change color. So you go here, you go here, right? So you have a 5 weighted inputs here. Inputs here 5. This is 5, and in this example you ignore bias. You ignore bias. So then you have this value by adding this input neuron multiplied by the weights, and this input neuron multiplied by this weight, and this by this weight, this by this weight, this by this weight. Of course, these weights are here randomly assigned. Randomly assigned weight. Then, as I told you, we're gonna find out. We're gonna update weights based on the training process, which consists of feedback forward calculations and back propagations. And we're gonna probably have to repeat that few 40,000-30,000 epochs in. Same thing our neural values obtained by similar manner, and here, but the number within this neurons are, as I say, temporarily or tentative. Why? Because the activation function is not applied yet. So if you take a look at the equations here, this is very simple. Node 1, I'm going to put the circle. Node 2 from a circle, 3 circle, and 4 circle. If you see here, this is a previous input layer, the neurons, input neurons, and this is all input neurons. When you multiply by the randomly assigned weights here, this is all randomly assigned weights, and this is previous neural input. And this is how you start with your calculation, calculating temporary or tentative neuron values in here. And this one should go through activation functions, and we indicate that f as a number here, and here of course the tentative values, neuron values. Okay, tentative neuron values, so that you pass these temporarily tentative neuron values to which activation function is a sigmoid activation functions. That means you put these numbers in here, so they get a new number which is final neural values here. This is final neural values. This is tentative neural values here. Okay, let me just put this. This is tentative neural values, and this is final neural values. How you're gonna pass the tentative neural values through the activation function, which is the sigmoid in this particular example. So this is how you apply your activation function to get them with a nonlinear responses, nonlinear behaviors that may exist between these inputs and these outputs. Again, this is one we saw before in previous lecture. I'm going to go and review again here. All the value here, highlight with green, is the tentative neural values. Now we understand what that means. And this is weighted inputs, and this is bias. So I'll say one more time. This part is weighted input. So you know these terms, lingo. When somebody says weighted input, then you have to think of this value in the matrix, and this is bias. Bias is not weighted. That's why they are not using weighted term to bias. So this is weighted input and bias, and these terms just simply indicates a temporary neural values because you are before the application of activation function. Now you're going to apply activation function. Whatever they are, you got here sigma. So you having a function value, when you go through the activation function, then what comes out here? Let me change colors here. What comes out here? It comes out with final neural values. So this all terms here, final neural values here, final neural values here, all terms here, final neural values, all terms here, final neural values. Okay, without sigma, it is a temporally neural values. Okay, and we are doing to every circle, every neuron. When we finish the feed-forward calculation, we probably could say that feed feed-forward calculations. Feed-forward calculations means you start from the input and do the same thing, repeat the same thing all the way to outputs. It's better to explain here. Here, you start from the beginning. You start from the beginning and through all the layers, and then you're going calculating the, say, first output. And this process is called the feed-forward calculations. Okay, this is very important lingo. Don't forget. Now, once you find out first output, and after finding as well the error functions or cost function, you're going back from the end to the first layer to revise your weights and bias based on error functions and based on chain rule. We're going to explain that later, so that once you're doing this and then you find out how you're doing with the revised weights and biases for next iterations, to see if how much your error or differences reduces. So this is a one epoch and this is another epoch. You're going, and then you're still having I'm sure that you're still having a weights and bias errors, and you're going back and redo to revise your second round of revise your weights and biases based on chain rule again, and then you check, and this is called the second epoch, and you check if your feed-forward calculation produces enhanced results, and you repeat this. So, to my experience, as I said, based on reinforced concrete design, you may repeat 20, 30, 40,000 epoch. It is a very lengthy process, and each iteration is called a epoch. Right? We see here first matrix formulation, first power of feed-forward calculation with related to the first hidden layer, and here we have a feed-forward calculation associated with a second hidden layer, and you have to repeat this feed-forward calculation up to the last upper layer. Okay, this is a feed-forward calculations, and the network that makes this feed-forward calculation possible is called a feed-forward network. Feed-forward network. So we learned a few lingos today, and which are very important for us to understand neural networks, and especially when we're driving a neural network, when we're formulating neural networks, when we're training neural networks, when we calculate it based on feed-forward calculations and backpropagations.